Hi everyone, welcome to this new video lecture of fluid mechanics. In this lecture, we'll discuss the continuity equation in cylindrical polar coordinates. In our previous lecture, already we have discussed the continuity equation for Cartesian coordinate system. So in this lecture, we'll derive the equation for cylindrical polar coordinates. So first of all, we need to understand what is this polar coordinates but Cartesian coordinates already you have discussed in the previous lecture. Okay, so let me give a brief idea about the polar coordinate system. So this is nothing but if you consider a axis is in y-axis. Suppose this is the y-axis and this is x-axis. And for the polar coordinates, if you consider, let's consider a point here. Okay, and this point location, suppose a P point is there, and this P point location from this origin point, how we need to describe this or how it will be located. Okay, this P point will be given like some distance need to be mentioned or some marking need to be given for this. So for this P point for this polar coordinate system, we can mark or we have to mark in this way like r and theta. So r is nothing but the distance from this origin point to this P point. So this is the distance from this origin point to this P point, and this theta is the angle. It's angle between the x-axis and the point of location here. So this is theta. And while marking this this one, we can mark horizontally what is the value of this and vertically what is the value of this. So these things well, like suppose we want to resolve the forces. Similarly, this also we can, if you want to find out this length from here to here, so that can be, we can mark it r cos theta, and similarly this vertical one we can mark it r sin theta. Okay, so this is about the polar coordinate system. Okay, but if you go for the Cartesian coordinate system, in that way, in that point we supposed to mark like P point is nothing but x and y. Like from x-axis how much distance is there and y-axis how much distance is there, that point need to be marked. But here it is slightly different. For the polar coordinate system, we need to mark in terms of radius and angle theta. Okay, so this is the concept of this polar coordinate system. Now for this we have to find out the continuity equation for this. So let's consider a small fluid element. Okay, and this two-dimensional polar coordinate system. Okay, this is the polar coordinate system, two-dimensional we have taken x and y, and this polar coordinate system need to be marked in, as I told you, r and theta. Okay, so a point location what we have taken here, the started from this O point. Okay, this origin point you can say, or which is we used to mark it O point, and the distance of this point, like suppose it is a location of what we have taken here. So this is one point and this is another one, and this fluid element, what distance is existing here with a distance of r. With a distance of r it is taken, and you can see this is the radius of this point location, and AB is the radial part of this. Okay, and it's moved with an angle of theta with respect to x-axis. Okay, and this is the point location of CD, and this is AB. And now if you consider this small part of this, okay, ABCD, and I'll tell you what is the mass of flow is moving in this radially and what is the mass flow is going out radially at this point location. So first of all, we have considered this two-dimensional polar coordinate with r and theta. Okay, and consider this fluid element. We need to consider the fluid element. Let the fluid element is ABCD. This is the fluid element what we have considered here, ABCD. Okay, this is the fluid element structure is there. If you want to draw, let me take it outside and it will be like this. Okay, so this is A and this is B, this is C, and this is D point. Okay, so these are the point location of this fluid element. which was moved or given in this polar coordinate system. And the angle between this, you can see the angle between of this fluid element to this x-axis is given with an theta, and the angle between these two, like AB surface, BC surface and AD surface, you can say that is d theta. So this fluid element center, that is d theta, is the angle between these two. Now the component of this velocity, okay, the component of the velocity which is at this region, which is crossing this AB surface, we can say that is UR, okay, and in radial direction of theta, and tangential direction, that will be theta. Okay, so we can write the velocity r UR in the radial direction. Radial direction means in this direction what we are considering, only this direction, okay, radial direction. And the velocity in the tangential direction. Tangential direction is nothing but, like, this is the fluid element, suppose what we have taken. So this is nothing but the radial direction what we have taken. So the fluid element, suppose here UR, and if you consider this one in a tangential direction, so that we need to consider U theta. Okay, so these are the two velocity component, UR and U theta. So here we need to find out first the mass of fluid which is entering in this side, like radially and tangentially. This is the work for us. Okay, so what we'll do, first we'll identify the sides. What are the sides are there? AB, BC, CD and AD. So the side of the element of length, we can say what is the length of this element, what is the length of this element, and what is the length of this element. Let's find out. So the sides of the element are having length. We can write AB, one side is there. So length of the side we can see that can be written in terms of r and theta. So what is the length of this? So that is nothing but the radius r is there. That means the distance from here to here, that is r, into the d theta. The d theta is the angular value of this. Okay, so that is r d theta. Similarly BC we have seen already, it is given dr. So BC length is nothing but, we can write BC equal to dr. And similarly DC or CD is the exist part of this fluid which is moving out. So that one we can see r plus dr into d theta. That means here r d theta is there, and if you go to the CD point, which is a distance of dr from the B point to C point. That's why the distance of this, or the length of this CD is r plus dr into d theta. And similarly this is AD length, we can write AD length also dr. What is the BC length? Same equal to AD length. Okay, so first one, what we will do, first we will find out the flow in the radial direction. We need to calculate two things, flow in the radial direction and flow in the tangential direction. So first I will calculate, or I will derive flow in radial direction. Flow in radial direction, this is the first point we need to derive. Then we will go for the second one. So to calculate this flow in the radial direction, first we need to identify the mass of fluid. So the mass of fluid which is entering at the one side, which is entering which side? Let AB side. The mass of fluid which is entering at the AB side. So what we know the formula for this, mass of fluid at AB, entering at AB per unit time. Per unit time we need to consider. So we know this formula, the mass flow rate, this is nothing but mass flow rate, mass of fluid per unit time. Okay, so this one we know that rho A V. So what is the density of this fluid which is entering here, what is the area of this, and what is the velocity of the fluid of this. Okay, So this one we can write rho into the velocity. Velocity in this radial direction we have seen, that is nothing but u into r, and area of this surface is nothing but the length of this into the thickness of this. So thickness of this fluid element, let's consider that is unity. The thickness of this fluid element, let's consider unity. So you can write AB into 1. So AB length surface already we got r d theta. So that one we can put the value here. So rho into UR, in the place of AB we can write r d theta. Okay. This is the mass of fluid which is entering at the surface at the side of AB. Similarly, we need to find out again the CD surface, because here what is the mass of fluid is entering, it will be relieved at this outer zone of this. Okay. So this is the part or the value of which is existing here. Let's see. So next point we need to find out the similarly the mass of fluid, okay, leaving here, there it is entering, here it is leaving, CD per unit time we can write. Similarly here also same formula will be there, rho AB, and rho AB here also density will be as usual, density of the fluid, and area of this surface, area of this CD surface, that is nothing but unit thickness is there, and into this surface value, okay, into the velocity. So here also you can write rho into UR. The value of CD you can write area CD into 1. This is the area, and what is the velocity value here? Now here it is UR, but here if you see the velocity R plus dr, because this is the distance traveled by this fluid through this surface. So that will be R plus dr. And if you see the velocity which is existing here, this is r plus dr into d theta, that is the actually value of this length of this object. But the velocity which is traveling from here to this surface, ur will be there, as well as we can write ur plus del ur by del r into dr, because that much distance is traveling dr, and this velocity ur with this total area it is covering, so that will be written in terms of derivative del ur by dr. So the same thing we can write. Yeah, now let's write, this is the density area, then velocity term we can write. What is the velocity here? We can write now already existing velocity ur plus del of ur with respect to del r into dr, the distance traveled. Okay, this is the velocity which is crossing this surface. Now if you resolve this force or resolve this mass of this fluid, we can write, rho CD value we can write. CD value is the r plus dr into d theta. So let me write that r plus dr into d theta. This is the value of CD. Okay, and into we can write ur plus del ur by del r into dr. This is nothing but rho into a into v, that only written. So area, I just kept the value of CD. Okay, now next we can write, just to resolve this total equation, okay, rho into ur, okay, ur into r plus ur into dr, okay, and plus we can write r, here r is there actually, r del ur by del r into dr plus we can write del ur by del r into dr square whole bracket, give it give this a whole bracket of d theta. Okay, so we can write like this. Now what we'll see, this dr square, we can get it, we can just neglect this value dr square. So this is actually very small, so you can just neglect this. So you can, what we'll get here next, rho into ur into r plus ur dr plus r d del ur by del r into dr. Okay, so this is bracket theta, d theta. Okay, now this term is actually very small, this dr square part. So that's why what I did, I just ignored this part. Okay, this is very small, that's why I have neglected this. So this is the mass of length in CD per unit time, and this is the mass of fluid AB per unit time. This is leaving and this is entering. Now we can find out what is the gain in mass. You can write what is the gain the mass in radial direction, or you can write in r direction per unit time, per unit time. So what we will do, just what is the fluid mass through the fluid which is entering at this AB side, that means this value minus this value will write. So that is nothing but the mass through AB minus the mass of fluid through CD. Okay, so what the value we got, just to write the value there, nothing, rho ur, this value ur r into d theta. Okay, minus, you just expand this, we can write rho u r d theta. I've just expanded this value. Okay, minus, we'll get rho into that, let bracket start here. So ur dr, okay, plus del ur by r, or you can write this is del ur by del r. Okay, into r is there into dr d theta. This equation what I have written here, just I have copied here the same equation. Now if you see this equation is going to cancel here. So finally what we'll get here, now minus rho, okay, just to give a square bracket here. Here also you can give the square bracket also. So square bracket start, ur divided by r. Okay, and ur divided by r plus del ur by del r, bracket close, d theta is there. So what I did here, I just took the r dr common and outside. Here see, r dr I have taken, but r is not there, that's why ur by r. Dr is there, dr I have taken out. And here if you see, r dr is already there, r into dr, so dr I have taken outside. So as usual, del ur by del r, del ur by del r. So r dr I took it outside. So this is the equation for this. So I let this equation, because this is going to use in the next case. So this is the thing, what we got, the flow in radial direction, okay, in the r direction. Next what we need to find out, the flow in the theta direction. So next step is for us, we need to calculate, or we need to derive the flow in theta direction, in the theta direction. So So here also simple. Again, we need to see the previous diagram. Now you see the theta condition means this is the entry part u theta which is entering here, and the value which is leaving at this side, AD side. So entering this at BC and suppose leaving AD side. Okay, tangential condition. So for that again we can write the gain in mass directly. Let's write out. Let's directly write the gain in mass theta direction per unit time. Per unit time we can write directly what is the mass through BC point. Let's see again what is the mass through BC point, this one, this BC point, and what is the mass through AD point. Okay, mass through BC minus mass through AD bracket we can write, and this is per unit time we can write like this. So directly I'll write the formula here. What is the mass through the BC? We know that rho A V, so that is nothing but rho into V into rho into A into V, the velocity through BC. Similarly minus rho A and the velocity through this AD surface, AD side. So we can write density, density as usual will be there, and area part we can write area of this, let's see the surface here. Yeah, if you see this surface, the area of this, that means the length of this object, that is nothing but dr, and what the unit thickness of this fluid element. So that is nothing but we can write area dr into 1. This is the area, and what is the velocity of this surface at this point? So that one tangential velocity u theta. Okay, so this is the mass through BC point. Now we can write the mass through the AD point. Similarly, we can write by seeing the above equation, we can directly write this is rho dr into 1. Okay, and this one we can write u theta plus del u theta by del theta into this is d theta. D theta, the angle it's traveled. Okay, bracket close, and just give a square bracket of this. So the total we can give a square bracket. This is the mass through the BC. Okay, and this is the total, the mass through the AD point, rho into dr into 1 into u theta plus del u theta by del theta into d theta. Now we can just resolve this or just expand this one. What we'll get, now see, this is let me write here, this is rho dr u theta, and now this is rho dr u theta, this part only. If you open this bracket, only this part will be, so this and this is going to be cancelled here. Okay, so what is the remaining part will be there? So remaining only this side will be there. So along with the rho dr in multiply of this one. So directly I'll write it minus rho into du theta by del theta into, you can write d theta bracket close into the area dr into 1. This is a minus. Now again what I'll do in this same thing, just I'll keep it, I'll just multiply something here. So rho del u theta by del theta into r I'll multiply and r I'll divide, r d theta into dr, as usual it is there. So what I did, just I multiplied r and I divided r in this equation. Okay, so up to now I think you have clear flow in the theta direction. Okay, now again similarly in the previously how you got the total gain in the fluid mass per unit length or per unit of this time, here also let's find out the total gain in fluid mass, the total gain in fluid mass per unit time. Okay, so this one what we can write, see this total gain in mass fluid per unit time is nothing but, so what is the fluid mass gain in the radial direction and what is the full fluid mass we got in the tangential direction. So both need to be written. So this is the equation what we got here previously, the gain in mass, okay, in the radial direction. Similarly, the gain in mass directly I have written here in the theta direction. These two things we need to write here. So total gain in fluid mass per unit time, okay, that we can write the gain in mass, the gain in mass in radial direction minus the gain in mass in theta direction or in the tangential direction. So just write this two equation value, how much what we got there. So previously I just got this one equation, rho into ur by r plus del ur by del r into r d theta dr d theta. Okay, so now you can write rho into ur by r plus del ur by del r bracket close r dr d theta. This is the value for the gain in mass in the radial direction minus this equation. Okay, minus we can write here, we can write here rho del u theta by del theta into r into r, yeah, rho into del u theta by del theta into r d theta into dr divided by r. Okay, this is the equation what we got. Okay, now this is the mass in gain in mass in the r direction plus gain in the mass in the theta direction, not minus, that is plus theta direction. So you will get this value, this is rho into this value in the direction of r, and although this value is minus here, so we'll get this one. Okay, so these things we can write here. So now next what we'll do, the mass of fluid element, the mass of fluid element, the mass of fluid element, we know that what is the value of this, rho a v. This is the rho a v. This one you can give a equation 1. Okay, this one you can give a equation 1 here. Now next the mass of fluid in element, that is rho a v, and here we can write, this is nothing but we can write mass of the fluid element equal to rho v, not rho a v, rho v, because we know that density equal to mass by volume, so we can write this. Yeah, next we can write what, rho equal to, as usual rho will be there, so volume we can write here, volume of this fluid element, that is nothing but r d theta into dr, the distance traveled, into the unit thickness of that. Okay, so this is nothing but we can write r d theta and dr. Okay, so now let's, this one you can bracket, you can write it. Next write down the rate of increase of fluid mass element, the rate of increase of fluid mass in the element, in the fluid element, with respect to time. With respect to time, what we can get, we just derive this unit, derive this value, that is nothing but del with respect to del t into rho r d theta into dr. Okay, this is the rate of increase of fluid mass in the element with per unit time. So what is the mass of the fluid element we got? Just to derive this value, we'll get this rate of increase of fluid mass. So now what we'll do, let take this rho outside. So we can write del rho by del t, del rho by del t into r d theta into dr. So this is equation 2. This is equation 2. Okay. So now we know that actually the continuity equation is based on the conservation of mass. Okay. And the conservation mass says that the mass is neither created or not destroyed, okay, in the fluid element. So what is the mass of fluid is coming inside, the same mass of fluid supposed to be leaving outside of that. Okay, there will be no created, no destruction will be there in the fluid element as per the conservation of mass. So the net gain of mass per unit time in the fluid element will be equal to the rate of this rate of increase of mass of fluid element. Okay, so this rate of increase of mass of fluid element, this should be equal to the fluid element what we got here previously. So what I'll do, this total gain in the fluid mass per unit time will be equal to this rate of increase of fluid mass in the fluid element. Okay, so both will be equalized. So you can write what I'll write here. Implies, I can start from here. Yeah, what is there? This is del rho by, yeah, that is there. Here minus is there. Yeah. So rho, what we got previously, bracket start, ur by r plus del ur by del r into r dr d theta minus del u theta by del theta into r d theta dr by r. This is the equation of this, the total gain in fluid mass per unit time. This one, just I have written that one, equal to, that means I am equalizing this equation 1 and 2, equal to del rho by del t r d theta by into dr. So now see, if both side, if you see r d theta dr is common is there. So what I'll do, I'll just directly cancel this r dr d theta in the both side. So we'll get what, and del rho by del t one side is there, and remaining terms are minus here. So let take this all these terms one side and make it the equation equal to 0. So del rho by del t plus, we can start from here. So that is nothing but rho into ur by r plus del ur by del r bracket close plus, okay, plus rho, yeah, rho is there, I have not written rho here, rho is there, rho del u theta by del theta, and divided by r will be there into, yeah, r by 1 by r equal to 0. This one you can give equation 3. This is equation 3, and just highlight this equation. Okay, so this equation actually what we got here, this equation is the continuity equation in polar coordinate system for two-dimensional flow. This is the continuity equation for the polar coordinate system for two-dimensional flow. I hope you understand. Del rho by del t, this is density with respect to time, and this is the equation actually, rho into ur by r plus del ur by del r. This is radial direction plus this is tangential direction, rho into del u theta by del theta into 1 by r, which is equal to 0. This is the general form of this continuity equation for this coordinate system, polar coordinate system, okay, and for two-dimensional flow. Now if the flow will be, if the flow, suppose a steady flow, if the flow is, just I'll tell you the condition. Our equation derivation is completed. Just I'll say you that what is the, if the flow is steady condition. The flow is steady condition means we know that del rho by density with respect to time, that is going to be 0. So what we can write, that equation what we got here, this part is going to 0, this part, okay. A remaining part we can write, that remaining part in terms of, we can write rho into del, radial direction was there, del r, sorry, del ur by del r into dr, okay, and no, only del ur by del r into dr into, sorry, plus ur by r. Actually this ur by r was initial, I confused, yeah, no issue. So this one plus we can write rho del u theta by del theta into 1 by r equal to 0, okay. So you no need to be confused here. One side will be there here for flow in the radial radial direction, and this will be for the tangential direction. Both should be there in this equation. Now again, what I'll do, I'll just take this rho common for this, both this equation. Then what I'll get here, I'll just can write del ur by del r, okay, del ur by del r. Here dr is not there. Let's see once. Okay, dr already you have taken, so only del ur by del r. So this will be not there, okay. Yeah, only del ur by del r plus ur by r plus, here we can write del u theta by del theta into 1 by r equal to 0, okay. So here what I have taken, just I have taken the rho outside from both these terms. This is one term, this is one term. For both this term I have taken this rho as a common and kept it other side, right side of this part, that is 0. So here I can write like this, correct. So next what I'll do, del ur by del r, and here what I'll do, I'll just r, I'll take it common out. R, if I take it common out, then what will be there here, r will be going to be multiplied in this, and here r is going to be cancelled. Just have taken the r common outside here. Now r common if you are take outside, so that will be ur r d del ur by del r plus, now see here also the r is going to be cancelled here. So del u theta by del theta equal to 0. So what I did in the sense, I've just multiplied r everywhere, common in the sense r everywhere. So what will be there, r multiply here, r del ur by del r. R if you multiply here, r will be cancelled, so only ur will be there. Similarly here if you multiply r will be cancelled, and here in this side if you multiply r also nothing, because 0 is there in the right hand side. So just you multiply r at this both of the side. Now if you see this equation, ur plus r del ur by del r, so that we can write derivative of r ur, okay, with respect to del r plus del u theta by del theta equal to 0, okay. This is your final equation, equation number 4 you can mention it, okay. This is nothing but we know the derivative of u into v, how we used to write the same thing I have written here, okay. Del of r into ur, if you derive in this way, that is the formula actually, we can write in this way. So this is the equation, continuity equation in polar coordinate system for the two-dimensional steady incompressible fluid, for the steady and incompressible fluid. Okay, incompressible fluid. This is the, we can write the continuity equation for steady flow and incompressible fluid flow. Okay, for the polar coordinate system. So I hope you understand how to derive this equation. It's very simple actually. Only you need to focus on these two terms. Okay, one thing we need to find out the flow in the radial direction. One is flow in the radial direction, another one is flow in the theta direction or in the tangential direction. Two things we need to focus, these two things only. Then for flow in the radial direction, what we need to consider? What the flow is having, like in this surface, in this AB surface, what is the flow is entering, and at this CD surface in the same direction. Okay, because this is the radial direction only we have taken here, R. In the CD, what is the mass of fluid is existing, leaving the surface of CD, this one. Then finally, what is the gain of mass in this radial direction per unit time. Okay, so what we got for the CD and AB, just to minus this one, we'll get this one. Okay, this is for the radial condition. Similarly, go for the tangential condition theta. So in theta also directly I have written the mass of fluid through the BC and the mass of fluid through the AD. Similarly, if you see, this is the BC and this is AD. So what is the mass of fluid which is entering here and what is the mass of fluid which is existing at the other side. And similarly, the formula what we finally we get this gain in mass in the theta direction. Directly I have written this one. And next we'll find out the total gain in fluid mass per unit time. Like previously what we got gain in the mass in the R direction plus gain in the mass in the theta direction, what we got. Okay, so just to put the value here, this is for the radial direction, this is for the tangential direction, and finally we'll get this equation. If you just resolve this one, finally we'll get this equation. This is our actual general form of this continuity equation for the polar coordinate system for the two-dimensional flow. And if suppose this is the density with respect to time, if the flow is suppose steady condition, then we can consider that del rho by t equal to 0, and we just solve this equation, we'll get this. So I hope you understand this derivation. This is a little bit lengthy, but I hope you understand. If you are having any kind of query regarding this, you can give a comment on the comment box. Thank you all.